thank you very much for the introduction, and thank you very, very much for giving me the possibility to present here today. I hope you all can hear me behind. It's now a challenge to keep you awake for another hour at 5 o'clock in the afternoon. I will try my best, and I will start skipping slides when I see more and more closed eyes in front of me. Here's what I'm going to talk about, but let me first introduce my co-authors. I'm going to give you an introduction and then zoom into two projects that I did recently. One with Gary Chapo, he's a PhD student at Maastricht University, and the other one with Hemant Bhargava and Gerle. And the nice thing is about Hemant Bhargava, with him I worked already 20 years ago on this, cloud computing, or what we called then decision net, or online internet computing platforms for accessing software there. So there's a link here to that part again, and so we got back to each other, now working on different topics and defining a new topic here. I will start a bit very broad on economic engineering, how I define it, and it's kind of a provocative term. It's actually, I googled it yesterday. It's not you can't find much on it. You find maybe engineering economics, but that's something different. Then I will zoom a little bit into mechanism design. So in contrary to Alex's talk, I will talk on a different aspect, so it complements nicely, where the focus is much more on designing the games rather than analyzing the games. And try to make that clear and give you examples of that. And then I give you a summary of two papers, one on that's published already, Selling a Public Good, and give you a little bit an idea of the techniques there, and I try to show you how they relate to mathematical programming. So what is the role of what I did in my PhD, namely integer linear programming and combinatorial optimization? What is the role in this mechanism design there? And then I zoom into multi-item auctions, which has very nice applications. With exclusivity margin, I will show you what we do there. There we do actually less integer programming, more simulation, more heuristics, with some nice results, we think. Some recent developments in economic theory. Now, I think it is fair to say that economics or economic theory was traditionally more descriptive. They used game theory, and they used other mathematical models, but it was mostly to understand how the world works, how the economic world works, to explain what happens in the financial markets, to explain what happens when companies take particular strategic decisions. So by that, economics tries to be informative for business analysis and also in economic policy. And the kind of instruments that are informed by economic theory are, for example, legislation, all kinds of tax legislation, taxation rules, also regulating markets, but also contract theory, for example, how to contract with your employees, what kind of contracts stimulate which kind of effort. But that was all more descriptive, and you saw contracts emerging in the real world, and game theory and economists try to understand why do these contracts make sense, or how should they be changed, or what kind of behavior can we expect if the contracts are as such. Now, in these kind of settings, the real behavior of economic agents is hard to predict, because these contracts are kind of loose. I mean, you can always have a lot of strategic behavior. Now, in recent times, and that I'm talking about the middle of 90s, more and more contracts or markets or kind of economic interactions were driven by IT, implemented by information technology, or in some extent implemented by algorithms. Here are a couple of examples. Auction and procurement systems. Well, one of the driving forces for investigating auction theory, for example, by computer scientists, was the emergence of eBay. But there were also other huge auctions that were generated in like 15 years ago. I don't know whether you ever heard about CombineNet. If there are artificial intelligence researchers among us, they might know the name Thomas Sandholm. He's a professor at Carnegie Mellon University. And he founded a company where they implemented combinatorial auctions, and that was used for procurement such as the total transportation over a year of IKEA worldwide, or of big European chemical companies. They had to hire the most advanced integer linear programming experts to solve the mathematical problems there. And I was talking once to one of them. They said we never had as such big problems to solve as in Thomas Sandholm's company. So that was an innovation that was possible because of new developments in IT, and where huge markets, huge procurement markets could be implemented. Ad auctions. These are the auctions that basically determine which ads do you see when you go on Google, or on Yahoo, or on all kinds of websites in the meantime. I don't know the recent numbers, but a couple of years ago, roughly 95% of the revenue that Google made was by selling advertisement. And we're talking about billions of euro here. Another example is Reply. That's a company with whom we work together now a little bit, so we are in discussion with them, and actually their auction format is basically the basis of the motivation for the second paper that I present. Reply sells customer leads. So basically consumers who are searching for example, used car, or searching for buying a house in a particular area, leave their data there, and then Reply.com auctions that data to car traders in the region. And the car traders make a bid to get that lead, as it called in marketing terms. The business for leads, for selling online customer leads, had a volume of 1.6 billion US dollar in 2012. So we're talking about auctions that generate enormous revenues. I don't think that Reply.com had all of that, but they're one of the market leaders in that business. Another example which is emerging where economists work in a different way are matching markets. And the most prominent one is probably, you might have heard about it, is the organs. So people who need an organ because of a medical problem, like a new kidney, it's often difficult to find matching people. They have nobody within the relatives. Now, an organ market does the following. So if there are two people who need both an organ and their relatives would like to donate, it could be that the relative of the first person could donate because of its blood group to the second person who needs it, and the other way around. So if you cross them, you could get a match. And Al Roth from Harvard University was really pioneering over the last 10 years the US market, clearing market for these kind of organ donations. It's not a market in the sense that anybody has to pay. That is certainly completely forbidden, even in the US. But it's a market that is a market in the sense of a market without money that increases tremendously welfare, and he got a Nobel Prize for that 2 years ago. And the same was for schools, matching kids to schools, or doctors who need a traineeship after they finish their studies. I could name reputation and recommender systems on eBay that are important design issues where economists can give design advice, and even social networks. And this kind of area in economics has gained two groups a Nobel Prize recently, and years before also to Vickrey and also to Nash, who are all a little bit in that domain. Now let's look at theoretical computer science. I think the big changes, and Alex has already mentioned that so in previous times, computer science or theoretical computer science focused more or less only on algorithmic issues. Maybe data structures, maybe databases and so on, but it was somehow always algorithmic, be it distributed or not. What now is new is really a need to model user behavior in the system, to have models that include models of user behavior. And by that, equilibrium concept, game theory, and so on. Because it is mostly because on the internet, many algorithms implement economic interaction, be it with or be it without money. So like routing, and I can repeat the same examples that I had before. On the other hand, there is also a need for an understanding suddenly. So Christos Papadimitriou said once, I think it was in Dachstahl in the wine cellar, that it's also now very interesting that computer scientists have to study the systems, the computing systems, in a way like the economists wanted to understand the economy, because it's not really clear why the internet emerges like it emerges. It's very difficult to understand why social networks emerge like they emerge. It's not because there's all this human behavior in this and all this dynamics that comes up. Now, also that was acknowledged, the work here in the new work in theoretical computer science. So as you might know, Koutsopias, Papadimitriou, Koutsopias and Papadimitriou for their work on congestion, on price of energy, on congestion games, let me be careful, and Nissan Ronen for their work on algorithmic mechanism design, and Rafgard and Tardosh also on congestion games, who got a Gödel Prize in 2012. So that's a little bit the development that happens since 15, 20 years. So you see a move from economics into computer science and the other way around. Now, the term economic engineering is, for me, capturing that getting closer in a good way. It's on the interface between theoretical computer science and economic theory. From the computer science and mathematics, the ingredients are game theory, combinatorial optimization, complexity theory, algorithms and data structures, even up to cryptography and more. And from the economic side, you have a lot of theory of incentives that was built over the last 30, 40 years. The whole literature on auction design, mechanism design, social choice theory that deals mostly when, for example, that covers all the voting theory. It's not just economics, it's also a little bit political theory in here. The whole economic part of matching markets, matching literature that is there, which more or less belongs to social choice theory. But also nowadays behavioral economics. So where you try to, at the first place, have mathematical models of real human behavior, including risk, including other regarding preferences, but also the experimental study of real of economic behavior in a laboratory, where you put students in a laboratory and you test the theory in terms of how they behave, but also field experiments. So these are the ingredients from both sides that come together, and the fields that we see are the algorithmic game theory, the title of the colloquium today. Related, not really a subset, closely related is computational social choice theory and also algorithmic mechanism design. And the rest of my talk will be about algorithmic mechanism design. Yeah, you might argue whether it is a part of algorithmic game theory. Depends a little bit, I guess, on whom you ask. So what is mechanism design? It sounds again like engineering. And probably because I do mechanism design, I get all these emails who invite me to engineering conferences or mechanical conferences recently. It can be also pure spam. Maybe there's something behind it. So mechanism design is the following. You have a government or a company, which we call the mechanism designer, that wants to decide on an allocation of resources, on allocation of resources, on some investment, building, establishing a public good, or whom to give some resources, whom to let drive on which roads. So it's about in a broad sense, an allocation of resources. Now, it wants to do so by designing a mechanism. And to connect to Alex's talk, designing a mechanism is designing a game. The game is played, and at the end, when all the players have chosen their strategies, you know how the resources are allocated. Now the problem here is that the mechanism designer has to deal with asymmetric information. So the players in the game, or the participants in the market, have private information. Their preferences over outcomes are their private information. All what the mechanism designer has, and also the participants in our models usually, is a prior. So they have a kind of idea how are the preferences distributed? How are the values for an item that is on sale distributed? With probability 1/2 5,000, and with another probability of 1/2 10,000 euro, to make it very simple. So a mechanism is then a game that determines an allocation. And now what's happening is it's a game form in the sense, and once the players come into the room, and we talk then about players having a particular type, so the preferences are now known. Now given their preferences, the players start to play the game. And then you get an equilibrium in the game, hopefully. Hopefully there are few equilibria. And now the mechanism designer wants to design that game that ideally, for whatever preferences the players have, the equilibrium is good. For example, that the social welfare is high, or that he earns a lot of money. That's the topic of the two papers that I explain later. The mechanism designer wants to make as much revenue in expectation as possible. Now, I give you a very simple example, the classic one, for which also this revenue maximization is solved. So there's a seller who wants to sell a single indivisible item, like a painting, say. The buyers have private valuations for the item, and the valuations are identically, independently distributed according to some probability distribution. That is known to the seller. Now, given that situation, how should the seller auction the item to maximize expected revenue? Now, that has been solved by Meyerson in a paper in 1981, for which he got later the Nobel Prize. The maximum revenue among all possible auction mechanisms that you could ever imagine is simply calculate a reserve price where you use the information about the prior. So for every prior there is a reserve price. Announce the reserve price and run a weekly auction. Or you could also run an English auction. Increasing price English auction where the minimum bid has to be at least the reserve price. If nobody makes a minimum bid, then the auction is held by the seller. So he has to somehow incentivize the bidders to participate, and he has to take the risk that he cannot sell it. But that is traded off by the reserve price, that he will, if it is sold, he will get always at least the reserve price. And Meyerson, in a beautiful paper, he could show that this is the best auction. You cannot do better. And there are various ways to implement it. And the nice thing in this auction is you have also a very good prediction for the equilibrium. Think of the English auction. If your value is higher than the reserve price, you would never step out as long as the competitors don't bid more. So you will be truth telling. You are incentivized to stay in the auction until the price reaches your own value. So that's what we call truth telling. So it has very nice incentive properties as well, very strong ones. Okay, you still with me? Now I show you give you introductions to two papers, or show you results on two variations of this single item problem. Believe me that if you try to extend the single item auction problem a little bit beyond selling several items or allowing for correlated information so that Alex value, if Alex value is higher than my expected value is also higher, or selling several items and you have complementarities, so you're selling two pictures, and if you get two Picassos, you want to pay more than if you just more than the sum for one or less, or so these kind of, if you make the setting a bit more, the preference world a bit more complicated, then we are very much in the dark on how to maximize the revenue for the auction year. It's a very complicated, very difficult research field, and you have to make very small steps toward that, and these papers are, in a sense, two small steps. So the first problem is a classical economic problem, public good allocation. The second is motivated by reply, by this online lead auction site. Public good problem. So we have a single indivisible public good can be provided at cost C. Public good means if I provide the good, everybody can consume it. Think of building a bridge across a river, where if the city decides to build the bridge, everybody can use the bridge. Think of building a public playing ground or whatever. So, in that sense, public good. So the agents have types, as we call it, and in this case we even allow for just signals. Basically, Alex thinks, well, if the bridge is there, I would benefit in monetary terms 10 euro from it on average every month. I would say 15 euro. And suppose the real benefit that we both had would be the average of the two. Right? So his signal is somehow distributed, my signal, we know maybe they are, but the value is somehow a function of the two. So therefore we call that signal, and the type distribution might be even correlated. So my probability of a high value increases with this value. What we want to do is, what we solved in the paper, we determine the expected surplus maximizing deterministic ex-post individual rational ex-post incentive compatible mechanism. I give you the definition of EPIR and EPIC in a minute. Think it is getting the incentive point. And what we do is, we actually use integer linear programming for that. For those who are interested in complexity and algorithm, it's not going to be extremely efficient what we're doing. We're going to criticize it later. But in principle, it works. Integer linear programming. Then we have an initial integer linear program. We are then modifying it a little bit. And the nice thing is that the matrix that we get at the end is totally unimodular, which informs us also from an economic perspective on something. And then at the end, I think I'm going to skip that part. I show you some examples to see how quickly we get there. Okay. So I need a bit of notation. So we have this set of agents that you still remember. It's again called N. You will still remember it hopefully from Alex's talk. Then we have this TI. Think of that is the possible signals or types that each of these agents can have. And then you have the product space over the TI is the total type space. So the combination of types that can occur. We have a probability of each type. That is just a discrete. This is not my laptop, so I cannot reply to Skype. We have a probability for each type. We have a valuation. VIT is basically the valuation that agent I has if the total type profile is T. And then we have what we assume is, and that is a typical mechanism design notation, this is all the types of the others except I. So if I look at I's value, given the others have that type, then I only assume that his value is increasing in its own signal. We are looking at direct revelation mechanisms, which means, and also Meyerson showed that that is fine, it means our mechanisms work simply as such. Everybody reports his signal, and the mechanism designer decides to build or not to build, and what everybody has to pay. That's a direct revelation mechanism. And we are modeling, to get into the integer linear programming stuff, we are modeling, we say xt is basically a decision variable, that is one for every type profile, many decision variables, okay, but let's live with it for a moment. And it's simply binary, it means if xt is 1, we're going to provide the public good, and if it is 0, we don't. And then everybody has to make a monetary transfer, and that's called PIT. That's the payment that I has to make if the total type profile was, or the total signal profile was T. Now, here is our objective. A mechanism is now given simply by, for every T, we have a decision. 0, 1. Don't build, build. So whenever we build, we have cost x times c, and for every type profile, we are going to decide on the sum of a payment vector. So that are our revenues, and that are our cost as a mechanism designer. That is the probability that that type profile occurs, and that we want to maximize. Now there are two constraints in our integer linear program. The first is exposed individual rationality. It simply says for every agent, for every possible type profile, the value that the agent has from the decision should be larger or equal than his payment. Otherwise the agent will not like our mechanism and might not participate. And here is exposed incentive compatibility. It means the following. It means I shouldn't lie. For every type of every agent and for every type profile, TI and type profile of the other agents, and an alternative report that agent I could make, the value, the utility that he has from the truthful report leading to the decision X of T and the payment per I of T is larger and equal than the value that he would have if he would pretend to be of type SI. So these are our constraints. Now the optimal mechanism design problem is maximize over all xt, over all possible x, this objective. So it's an integer linear program, just too many variables. But Meyerson has solved that problem basically for the auction case. And for the auction case it has a very nice structure, and I show you that for the public good problem it also has a very nice structure. Now, one thing that, I skipped that slide because this tells the whole story. One thing that we know from these kind of settings is the following. Suppose we have two agents. Here's the signal of the first agent, there's the signal of the second agent. In order to get the incentive compatibility right, in order to have a chance to get payments that incentivize the agents to tell the truth, we have to allocate in a monotone way. Meaning, if I fix the report of the second agent and look at the first agent, at some point I'm starting to build, to provide the public good. And that is the borderline. The red borderline is here on the borderline and beyond I'm going to provide the good, and below I don't. Now monotonicity means when I start to build the good and the agent 1 increases his signal, his report, I should still build. And that in both directions. And that is necessary and sufficient for implementability. That is nice, because we now know that the region where we have to set the xt variables equal to 1 is upper comprehensive. Now that is basically very nice. Now we are going to do a little bit of algebra. And that I'm going to skip for you, but I want to show it to you anyhow. this is, in another way, written down our expected revenue. And we have to twist that a little bit, and that takes a little bit of algebra and gets us here. And all what I want to tell you is the following. Here is my decision variable, here is my probability, and here is what we call in mechanism design a conditional virtual value. It's purely algebra. Now, but this is just, all what you see in here are just parameters of the model. It's the input of the model. It's a distribution, it's a possible valuation, nothing more. It's a constant. Now we get the following problem. Maximize this objective function with these parameters or coefficients of the decision variables, actually including the phi t, under the monotonicity constraint. And that is a graph closure problem. So basically think of my grid of possible value pairs as a directed graph. And there are old papers in combinatorial optimization that show that this problem can be solved by transforming it, even in more general settings, non-planar and whatever, transform that into a min-cost slope problem. What you basically have to do is, so for every decision here, you have this expected this coefficient there, and so every node in this graph has a weight, and you are searching for a set of nodes that is upper comprehensive, meaning that if you take that node, you have also to take any other node that can be reached from that node by a directed path. So that it can be solved in a polynomial time. It has many variables, but in this encoding it is polynomial. So that is basically the solution. So that we get this theorem, the surplus maximizing public good problem mechanism can be computed in polynomial time in this enormous encoding. And we also know that the underlying matrix is totally unimodular, and that informs us that a randomized mechanism could not achieve more revenue than a deterministic mechanism in this setting. And the whole thing works for correlated valuations, for interdependent valuations, so in a much more general setting than in auctions. It turns out if you do the same thing for auctions and you allow for correlation and for interdependent values, the problem becomes NP complete already for two bidders. So we have a contrary message here to a paper by Papadimitriou and a PhD student on the auction setting. Now, I'll check my time. Oh, yeah. Sleeping eyes? Okay. I dive now for 5 minutes a bit deeper to show you a little bit the richness of mechanism design on this topic. And then I wake you up again and we go to the reply example. Okay, let's dive. So far I showed you the solution for exposed individual rationality and for exposed incentive compatibility. It basically meant whatever other people you have in the room, whatever their types and their reports are, you should tell the truth. It's the best that you can do. Now, in economics, we have other nodes. That is sometimes extremely demanding. So you could weaken that. And that is what we call Bayes-Nash incentive compatibility. Now we say, telling the truth maximizes your expected utility. And expected with respect to the possible distribution of types of other people that you face in the room. So you have uncertainty, but you want to do something that is best for you in expectation, given the kind of people that you're getting today in your decision room, in an auction or whatever. The same for interim individual rationality, meaning only in expectation you want to go home without having paid more than you value the outcome of the allocation. So that is a definite weakening of the incentive constraints. Now how does that, what happens in our setting? Well, there's one very nice paper recently on these one-dimensional mechanism design problems, by 5 authors, Gershkov, Gore, Kushner, Moldovano, and Shi in Econometrica 2013, they could show that in a very large class of settings, the best Bayesian-Nash incentive compatible mechanism or the best dominant strategy incentive compatible mechanism is always as good as Bayesian-Nash incentive compatibility. You don't gain by relaxing the constraints. Very nice, very deep paper using some mathematical theory from optimization, convex optimization. But you require here that there are now informational externalities, and you require that the types are distributed independently. And that gives us, if we make this strong assumption, also the same. So we know actually that our mechanism, as a corollary of that, is the best Bayesian-Nash incentive compatible mechanism as well. And just note that problem was already solved for independent types and in particular distributions by Güth and Helbig in 1986 in a paper. Now all that breaks down this equivalence when I either drop IID or informational externalities. And here I want to give you a bit, and therefore I really want to leave that part in. I want to give you a little bit an idea how these mechanisms can look like. So here is, and don't have to read the text really. Suppose I have two agents, and here are the possible type signals that the agents have. So it's either both are of type 1, or one is of type 1 and 2, or both are of type 2. So here is the optimal mechanism that our algorithm computes. It says, only build the project if both have type 2 and charge both of them 2. Actually, by the way, we also need to have these probabilities over here. And you see the probabilities are now that the probabilities are correlated. The distributions of both types are correlated. So in that setting, this is what our mechanism would do. Here is the best Bayesian-Nash incentive compatible mechanism. And it is quite strange in the following sense. You would say if both are of low type, value with a good low, you allocate and you charge them both 1. If one is of high, one is of low, you don't allocate anymore. You start allocating again if they are both of a high type. And then you charge them 1.75. You cannot charge them 2 anymore, then you get an expectation, not anymore expected individual rationality. So this is a mechanism that you get again out of Bayesian-Nash incentive compatibility, and but it is kind of odd, right? How would you tell people that it's not monotone, right? In the sense, if it happens that they both have a low type, you build, and then one says, oh, I actually have a high type, no, then I don't build anymore. But if the other one also says I have a high type, you build again. So in that sense, you get more flexibility by this looser equilibrium concept, but at the same time you get also kind of irrealistic or strange mechanisms. The same happens here. That is basically with informational externalities. Now that is even more difficult to read. I think I skipped with that. But what you see basically here in the examples, that the kind of things that we actually compute, and that gives me then, and I skip all that. So let's look back what we achieved for the public good problem. We got the full picture in terms of varying economic requirements, assumptions, so Bayesian-Nash, interdependent types, and informational externalities, all that worked. We could reduce it to a very nice combinatorial optimization problem. If you would like to solve it, the input would be very big, so you get simply even for a fast combinatorial algorithm a problem. And the result of it is, in a sense, a complex mechanism. It's such a red line that defines an upper comprehensive area. Even in the dominant strategy incentive compatible case, it's just a table. It's a table that says you have to look up for every combination of types, build or don't build, and these are the payments. if you would have to explain to the bidders, as the politicians, you have to explain the way you decide on a public good, and you would have to say, well, this is my table, now tell me what you want. This would be undoable. So these are mechanisms that are not practical. And that is also a recent development in mechanism design that's coming up. Let's focus, guys, let's focus on simple mechanisms that are practical, that you can explain, that people can play, that they understand. And that is the second paper that I want to present a little bit. It's on multi-item auctions with exclusivity margins. Now let me get back to the reply example. So this company sells customer leads. Now the bidding there is a bit more complicated. What the company says is, as a car dealer in Paderborn or San Diego or wherever, or Los Angeles, you can say, I want to have a lead, but I'm fine to share it with two other companies, two other car dealers. Or you can say, no, if I get the lead, I want to have it exclusively. So you can make either a shared bid for shared possession of the lead, and then reply says, I'm not selling it to more than 3, or you can have exclusive access to that customer. Now, getting exclusive access gives you more power and higher probability that you can trade, so you have a marginal extra value for getting the good exclusively. So the question that we study is, how does the revenue maximizing way look like to sell multiple identical items to unit demand buyers who attach additional value for being served exclusively? Now, reply.com has, for whatever reason, decided that buyers can only make one bid, either exclusive or shared. Now, the first thing that you can do is you allow for both bids, but that is improving the situation. But what is the best way to do it? We don't know, but we know good ways to do it, and that I'm going to tell you. So this I can skip. There is actually a second application for that. Yahoo has Yahoo is experimenting of selling their ad auction, their advertisement links also this way, by letting companies pay or bid to get the exclusive link on a page and not share it with others. So it's the same motivation, same problem, and I think they have a particular format for that I have to confirm. I don't know exactly how it works, but they have a patent anyhow, so I shouldn't reinvent it. Now, so I said already, why is that problem now difficult? It is multidimensional, because now every bidder has two pieces of information. The value for getting the item shared, plus the extra marginal value if he's the only winner in the auction. So two-dimensional information. The integer linear program would again explode in size, and next to it, it would be difficult to analyze it because of the two dimensions. We would not have such a simple monotonicity property that we could exploit in the public good case. And we would be afraid to get complicated impractical solutions. So we want to have speedy solutions that are easy to implement. And what we did in the paper, we are simply analyzing some simple heuristics that hopefully provide good revenue. And what we also do, we still use the mathematical programming approach. So we model the optimization problem, and we show that there are relaxations of the problem, which are again one-dimensional. So relaxation in the sense that the optimal objective value is larger or equal than the optimum of our real problem. Now they are one-dimensional. Then they are not simple, it's still complex, but we can, for these one-dimensional problems, we can use recent theory to solve the optimal option for the relaxation. What we then do, we do a simulation, and by that we can get the good revenue. We can prove in simulations how good our proposed heuristics perform. So here are two very simple ways of, two simple heuristics. The one is we never sell shared. We only sell exclusive. So bidders only report the value for exclusive possession. We allocate at most one item. Highest bidder wins. If above a reserve price, pays the maximum of the second highest bid and the reserve price. Forget about allocating shared, and we can use the optimal reserve price from Meyerson's theory, and we get a heuristic. The other heuristic is we only sell shared. We always sell to at least two bidders. And then what we can use here are so-called VCG prices, Clark growth prices. It basically means you do a kind of externality pricing, roughly. What in such an auction, what you have to pay is the following: you pay the externality that you cause to the other bidders. So if many items are to sell, you are there, you win a little bit of that. Now and the others win also a little bit. Now suppose you would not be there, then your items could be distributed among the others. That would create more welfare among the others. Now take the difference. Take the welfare that the others would have if you would not be there. Subtract from that the welfare that you have if you are there. That's your externality. That is what everybody has to pay. That makes truth telling a dominant strategy. So that's VCG story. And tonight with the beer you can think about it why the second prize auction is exactly doing that. And then you know that you have understood what I was just saying. Okay. The other thing that you can do is you could use this VCG auction without reserve prices. So that would mean you allocate efficiently, given two-dimensional bids, and you do again VCG pricing. And then our best heuristic that we actually propose is to do the following. You do VCG, but you have for exclusive allocation and for non-exclusive allocation, you use from the first two examples the optimal reserve prices and twist by that a little bit the allocation rule of the VCG mechanism. Now it's getting too late and I also don't want to dive deeper into details. So that are the four heuristics that we have. Now here are the two ways to compute an upper bound. The first one is a simple trick. Both are simple tricks. The first one says, assume that one dimension of the private information is public. Assume that the marginal extra value for getting exclusive possession of the item is public knowledge. Everybody knows it. That means you don't have to take the incentive constraints for lying that information into account. That gives you a relaxation. So the nice thing is, for that problem, the optimal auction has been given in a paper by Deng and Package in 2013. So they wrote a paper on the very much same topic, but they simplified in the very beginning and said, well, assume we make the simplifying assumption that one part of the information is public. So we have a one-dimensional problem. The second upper bound that you can do is you give every bidder two personalities. There is this bidder who cannot decide, so split the bidder in two. There is one bidder, one copy of the bidder who wants to have exclusive possession, and there is another copy of the bidder who wants to have none, who is fine with the shared possession of the good. Let them bid independently. Now the valuation of the first bidder is the valuation of the valuation of the one that it goes for shared is the same valuation as its original, and the valuation for the one who goes for exclusive is the sum of the valuations for shared and plus the margin. So by that you get interdependence of distributions, but that is fine. You can still solve it in a Meyerson kind of way. So these are the upper bounds. Now we have a theoretical result here. The expected revenue of the maximum only exclusive or only shared auction is at least one-fourth of the expected revenue of the optimal mechanism. And we use these two upper bounds to prove that. And here is, more importantly, here are the computational results that we get. And that is almost the last slide of my presentation. this is only shared. So this is number of bidders. This is the fraction that you, the ratio, or the revenue to upper bound ratio. So that is the fraction of the ratio of the upper bound that you can achieve with these four auctions. So we compare the ratio to the upper bound that we computed, where the upper bound is the minimum of the two upper bounds of the two that I showed. So if you have a small number of bidders, and that is a distribution, that is uniform distribution, signals and marginal values are uniformly distributed between 0 and 1. Now here the picture is still relatively good whatever you do, except you should not sell only shared if you have a small number of bidders. If you sell only exclusive, it's fine. If you have a small number of bidders, you can make a lot of revenue, but if there are more bidders coming, you should not do that. If you do VCG, you're actually doing pretty well. It's even increasing in the number of bidders. And that is our mechanism, our heuristic mechanism that we propose. So it's here a bit below VCG, and here it is. And here it is, and for the rest it is above. Now for other distributions, you see that you can gain actually here much more. So for example, if you do VCG, and you have exponential distributions with a mean of 0.5, then if you do VCG, it becomes very bad in comparison to the upper bound. If you here for a 5 number of bidders, and then it's improving again. Only shared has the same pattern, but it is not. It's the ratio of the fraction of the optimal of the upper bound that you can achieve is much lower than for the other distributions. For only exclusive again, and that is what we achieve with our heuristic. So without solving really the problem, we can show that that a heuristic is doing pretty well, and by using the idea of relaxation and solving the relaxation optimally and throwing that in a simulation, we can prove that we get guaranteed more than 80% of the revenue of the optimal auction. It's not a theoretical bound, but it is, I think, from a practical point of view, a very informative bound. There are many other research, so that is the end of the second story. There are many other research problems in this field on optimal mechanism design. For example, if I give you any kind of optimization problem, and I say the data is somehow coming from agents and it's private information, can I incentivize the agents to tell me the truth? There are examples where you can never, where, for example, you cannot achieve you cannot optimize independent of computational complexity. You cannot get the total social welfare independent or the optimum if you have to incentivize to the agents to tell the truth. So even if whatever payments you use. So the question is there an approximate truthful approximate mechanism? How good can you approximate if you require truthfulness? Then we have a lot of research nowadays on, given a simple mechanism, what are the full information of Bayesian equilibria? What are others equilibria? Are there very bad equilibria? And so on. A complete characterization of implementable rules for multidimensional information is out of reach, missing. How to handle correlated information distribution, informational externalities, and so on. Overall, the design of simple mechanisms is a difficult topic. And then, once we would have solved all that, we would talk to the behavioral economists, and then they would tell us the behavioral assumptions that you make are completely wrong. People are other regarding. They are not selfish. They are not always rational. They are not risk neutral. They are not always profit maximizing. So whenever you so you need also behavioral experience. The connection to behavioral experiments is still missing, or is only slowly improving. And then if you go even in the theory part into what actually economists do in terms of implementation theory, mechanism design, they have many theories developed with belief updating and so on that were not looked at so far by computer scientists. So if one wants to go that direction, there's plenty of work to be done. So my conclusions then finally, I try to show you a flavor of economic engineering. It's, in my view, a very vibrant new research field, the interface of theoretical computer science and economic theory. There are a lot of new opportunities for computer science to contribute to the engineering of economic systems, and I think it's important. I think it's important that the systems that we engineer, if they are in a distributed setting, that they model the behavior of the users, in the strategic behavior. Interestingly, the economists get very excited as well about computer science. So if you talk, for example, to Paul Milgrom, who is one of the leading auction designers for huge auctions in FCC, all kinds of auctions, he's working a lot with computer scientists recently, and I think his company is flourishing because of that, because they get tools from us or from optimization that they didn't know before and that somehow are helpful to design. So it's also a spillover from computer science into economics. So new techniques for analysis become available. What we do so far is largely based on the assumption of fully rational profit maximizing agents, which is in contrast to many findings in behavioral economics. In auctions it's a bit okay, because even in the lab people behave a little bit like we predict, or mostly like we predict. But if you really want to design, engineer economic systems with computer science tools, ultimately you will have to do behavioral experimental validation, and I was happy to hear today from Alex that is also something that is going on in collaboration here with the economists here at the Heinrich Nixdorf Institute. Thank you very much. I'm at the end of my presentation. Thank you for your attention, and I'm happy to take some questions.